Lesson 1.4 is entitled Geometric Series. So we're going to review our previous concept, which was when Spider-Man was bitten, the radioactive spider injected 1 milligram of venom into his body. So that's going to be our T1, 1 milligram. We know that this is going to double every hour, so our common ratio is going to be 2. How many milligrams were in his bloodstream 8 hours later? So this is where we're going to have to do some thought. So here it says 8 hours later. If we're talking about 8 hours later, so this will be 1 hour later from term 1, 2 hours, 3, 4, 5, 6, 7. So term 8 doesn't correspond to 8 hours later. It's actually going to be term 9. So n equals 9 in this case. So when we're using the equation, it's going to be term 9, which equals our first term. So our first term is 1, multiplied by our common ratio 2 to the power of 9 minus 1. So the 1, when we multiply, doesn't matter, so we don't need to write 1. So we're going to write 2 to the power of 9 minus 1 is 8. So that's going to be 256 milligrams will be in his bloodstream 8 hours later. So the only trick to this is if they talk about time, we always want to add 1 to that to actually get the term numbers. So our new formula for this section of the lesson is called the geometric series formula. So this is where Sn equals, so this is to find the sum of the terms of a geometric sequence. So T1, we're going to multiply by r to the power of n minus 1 divided by r minus 1. Now, non-permissible values, r is not allowed to be 1, because if r is 1, then that would make the denominator 0. So T1 represents our first term. N represents number of terms. R represents your common ratio. Sn represents the sum of n terms. So what do they add up to? So in this case, they're saying determine the sum of the first 15 terms of this sequence. Because there's 15 terms, n is 15. T1 is our first term, and that is given, which is 40. To find r, we're going to take negative 20, which is term 2, and divide it by our term 1, which is 40. So that simplifies to negative 1/2. So this is what we can use to solve for the sum of 15 terms. So our first term, 40, multiplied by r to the power of n, so that's going to be negative 1/2 to the power of 15. We're going to subtract that answer by with 1. So subtract 1, and then at the bottom we're going to have to do negative 1/2 minus 1. Okay, so with this, we do have to follow BEDMAS very carefully and watch how we do this in brackets. So we're first going to evaluate this part of the brackets first. So I would suggest you take this part and put it in first, get the answer, and then multiply that answer by 40. So that would be the top of your answer. And then you would separately get the bottom. The bottom will be equal to, if you put 0.5, you're going to get negative 1.5 at the bottom. So whatever answer you get at the top, so I'm going to write what the answer was at the top. Okay, so you should be getting at the top negative 40 approximately. And if you divide negative 40 by negative 1.5, you should get that the answer, the sum of 15 terms, is about 26.67. So that is rounded to the nearest hundredth. Okay, so watch that you're doing this properly. BEDMAS is very key here. If you're not getting the answer, it's because you're not doing it properly. You're not putting brackets either properly. So what I suggest is you do the top separately, the bottom separately, and then you divide the answers like I did. Example number 2, there was a clip of a video where they give you this sequence. So I'm going to give you the sequence from the movie clip that I was going to show you. So this one is where your first term is 1. And then the question that I would ask is maybe when, at what stage, at what term will you reach 1 million people? So when will your terms add up? When will the sum add up to 1 million people? So here in this case, n is equal to 3 because you're multiplying by 3 to get from number to number. So you're using the equation from above to solve for the sum of an unknown number of terms. So we're going to put 1 million into our sum spot. And that's equal to 1. And then our r is 3 to the power of n minus 1 divided by 3 minus 1. So the 1 we can ignore because it doesn't affect us. So it's going to be 3 to the n minus 1 divided by 2. Now we're going to multiply both sides by 2 to get rid of that denominator. So that'll be 2 million now. And so 3n minus 1, we're going to add 1 to both sides. So now we have 2,000,001 is equal to 3 to the power of n. So a way to solve this is using something called logs, which you will more study in 30-1 and 30-2. So what we do is we put a log on both sides of the equation. And then what that does is it brings powers in front as coefficients. And then we can divide both sides by log 3 to isolate for that n value, which is the power that we're trying to solve for. So we have a button on our calculator that says log. So you just have to look for, on your calculator, log, and in brackets you're going to put 2,000,001. Close your bracket and then divide it by log 3 in brackets, close the bracket, and you should get about, the n is going to be approximately at term 13, so like between 13 and 14. So if you're at term 13, you'll be slightly under 1 million people, but at term 14, you'll be at over 1 million people. So kind of between those two values. So since it's number of people, we can kind of have an in-between stage, but we'll leave it like that as an answer. So in this next one, they're saying that there are 10 terms. So n is 10. And the common ratio they're giving us is -3. They want us to figure out what T1 is, which is not given. But they tell us that the sum of 10 is equal to -29,524. So as you can see, we have most of the information except for T1. So we're going to plug in -29,524, which is equal to T1. R to the power of n, which is -3 to the power of 10. And we're going to divide that right side by -3 minus 1. So -3 to the power of 10 is equal to 59,049, but we're going to subtract 1 right away to get 59,048. And then at the bottom, we should have -4. We're going to multiply both sides by -4 to get rid of that denominator. And we'll get 118, so 118,096 on the left side. And that's equal to T1 multiplied by 59,048. Now to get T1 by itself, divide both sides by this 59,000, and 48. So T1 equals, if you divide those two numbers, a nice number of 2. So that's your first term. Example number 4, calculate the sum of this geometric series. So here they're actually giving us Tn, which is our last term. So we're going to have to do this in 2 parts. We're going to have to figure out how many terms there are, meaning what our n value is first. And once we have our n, then we can solve for Sn. So we're going to use the original geometric sequence formula. So we're going to use what we did in the previous lesson to solve for the n, because we know that the last number in the spot is negative 46,875. Our first term is negative 3. Our common ratio is 5, because we're multiplying by 5 to go from term to term. And then our n is what we're trying to solve for. So we're going to divide both sides by negative 3, because you always get rid of that T1 to the other side first by dividing. So that's going to give us 15,625, which is equal to 5 to the power of n minus 1. Now this is where we're going to use common bases, because 5 to the power of 6, if you put that into your calculator, it can replace 15,625. The reason I do that is because if the bases are equal, we can ignore them and look at only the powers to help us solve for what n is. So if we add 1 on both sides, we actually know that n equals 7. So there are 7 terms in this series. So now we're going to solve for S7, the sum of 7 terms. So we're going to use T1, which is negative 3, multiplied by r to the power of n. R was 5 to the power of n, which is 7 minus 1. We're going to divide it by r minus 1. And if we put that into our calculator, you should get negative 58,593. Example number 5. So let's say a person takes an antibiotic to cure an ear infection. Each tablet contains 200 milligrams. So we know that T1 is 200. About 12% of the mass remains in the body every single time. So there's our R value. In this case, we know that that is what is left over in the body, and that's 0.12 when you divide that number by 100. So to find out 3 tablets, what is left in the body, because there's always a remaining amount left in the body once you take your new tablet. So the sum of 3 terms equals T1, which we know is 200, multiplied by R, which is 0.12 to the power of n, which is 3, minus 1, divided by R minus 1. If you calculate that, you should get that by 3 tablets, you have 226.88 milligrams in your system. And then the sum of 12 tablets. We have 200 still as our first term. We still have the same R value, but our N is now 12. So when we calculate this, we get 227.27 milligrams. So you'll notice that the amount isn't high. The reason being is that our body is ingesting a majority of the tablet and only leaving a small amount from the previous tablet, so it shouldn't increase too much as we take more tablets, which is good. And then our exit task here we're talking about an ancestral line where we have 2 parents as our first term, 4 parents as our second term, so our common ratio is 2. They're trying to figure out the total number of Caitlin's direct ancestors in 20 generations. So n equals 20. So we're just putting the sum of 20 into 2 times 2 to the power of 20 minus 1. So our term 1 multiplied by r to the power of 20 minus 1. So 20 was our n value. And we're dividing it by 2 minus 1, which is r minus 1. So if we put that into our calculator, we should get 2,097,150. So that is the total number of Caitlin's direct ancestors if we have 20 generations. Lots of people.